So, what questions do we have?
Yeah, you knew her fucking brother. Well, we saw apparently we saw Brittany's ghost with her brother. And fucking Hannah Express. Yeah, was that pretty person's brother? I'm like, how the fuck you know his brother looks like that weird?
Questions about organic chemistry, anyone?
Do you think we need another box? What is that box called?
Fatty acid biosynthesis. That's the like machinery that does the biosynthesis. What?
We need to know that.
I would say you should know the reactions that happen. I cover them super in depth in the office hours recording from April 16th. Oh, that's just my notes printed out.
Yeah.
Word. Hey, well, I just uploaded the ones from last night today. So oh, okay, word. Gotcha. I don't think you need to know exactly A through L, but like understand what's going on, because like understand the overview. So fatty acid biosynthesis is broken down into 4 steps. Like those A through L is like covering the 4 steps where it's, what is it, a Claisen and then a reduction and then the elimination and a reduction. Don't quote me on that, but it's in the notes. So you should know the like general pattern of that. I am of the personal belief that he wouldn't ask you to like draw out the mechanism of fatty acid biosynthesis, because first of all, it's time consuming and you only have so long for the exam. Second of all, that takes a lot of space. So I think he would ask you more conceptual questions that are like, how many NADH are required to make a C22 fatty acid? Or how many carbon dioxide are generated? Yeah, so each round of fatty acid biosynthesis requires 2 NADH and will create 1 carbon dioxide. But yeah, so the steps of fatty acid biosynthesis are Claisen, reduction, elimination, reduction. And both of those reduction steps need an NADH. Yes, because the first round, you use 1 malonyl-CoA and 1 acetyl-CoA. So every time you're adding on another malonyl-CoA that you decarboxylate. So that's where the CO2 comes from.
How many NADH did you say?
2 per round. Because each round has 2 reduction steps, and each of those requires 1 NADH. Yes, Helen.
I have a question about oxidation, but when something's going to oxidize, it looks like there's it looks like there's.
Okay, if you have a specific place you want to point me to and something you want to walk through, just let me know and we can go through it like step by step. So the computer here is muted. My iPad is not muted. So the iPad is collecting the audio and the visual. And then I upload it to YouTube. Yeah.
So it's
Please don't.
It's just on the study guide that you made this.
Yeah.
And it looks like there's, when we say like -2H plus, but when we're doing that, now there's like 4 electrons in each of those negative
I'm not following your question exactly.
Like,
Okay,
when we have OH, we have like the, yeah, and then it turns into like the bond. It's just, and each of those are two.
each of those is worth 2 electrons. And 2 electrons is the same amount of electrons that are needed in a bond. So basically what happens there when we do minus 2H is here, let me separate this. We're losing, so you can think of it as something else is coming and taking the proton, and those electrons are returned. Something is taking the proton, and those electrons are returned. So you get O minus, and you still have 1 proton here, but you also have a lone pair. Because when we draw out our bonds, we think of them as electrons, like that. And so the proton doesn't keep any of those electrons. They both go back to like parent atom.
Do you think it would be fair to say that like each of the H2 or whatever that translates like yeah, that when you say that's like generally equal to like 4 electrons.
You're not taking any electrons. You are just taking the protons.
What is taking the protons?
So this specific like drawing style is not indicative of what is taking the protons. This is just your structural reasoning and like the bookkeeping behind oxidation and reduction.
You just write that those two go through.
Yes. So there's a question like this on the exam on prelim 2, and you guys were supposed to do the structural reasoning because you hadn't learned the mechanisms yet. And so the structural reasoning is this like bookkeeping where you do the minus 2H and then the minus 2 electrons so that one of them becomes a positive. And then you have the creation of the final product. Yeah.
Example of a reaction point that, like, I mean, I guess the equivalent of the
I really don't think that that is going to be on the exam. So I really think that the exam is going to look, and this is not confirmed yet because I have not seen the exam. I'm waiting for him to hopefully send it to me so that I can maybe guide our study a little more, but that is up in the air right now. I think that you're likely to get questions from the homework, like the ones from the homework, where you have like a whole reaction scheme and it's like, what reactions are these? Or where you're given the starting material and the reagent and you have to draw what the product is. And I think he would probably use NMR to help reinforce those concepts of like, so you have the 2 that I can think of off the top of my head that give multiple products are addition to an alkene and electrophilic aromatic substitution. So those are 2 reactions where you could be getting multiple products. And you can use NMR to tell you which of those products actually happened. And so there's some practice problems like that on the NMR homework set. And so I think to really do like an overview of all the concepts, he would have a long reaction scheme like that where you end with 2 possible products and then he says, okay, here's the NMR of the product. Which one is it? But that is just my guesstimation.
you appreciate what it is.
Yeah. Mm-hmm. Yes.
You said they reached out and one else has multiple products.
electrophilic aromatic substitution. And that will have multiple products when you have directing groups. So like when you have an electronegative atom attached, so like when you have a benzene ring that has an O here, the electrons on this can direct. So like if we made this a double bond, this would push here. So if you were doing electrophilic aromatic substitution with this molecule, you would most likely see addition at this site and this site because of how the resonance structures go. Yeah. It would technically also go here, but these two are symmetrical, so they would look the same. Okay, acyl substitution. So this is, we'll go through question 3 from problem set 7. So in this one, he gave you a handful of reactants. Really, these are more R groups than reactants. And then you were meant to put them together to create an acyl substitution. So the first step in doing a reaction like this is identifying what you need to do an acyl substitution reaction. And so our important steps for an acyl substitution reaction are we need an acyl and we need a nucleophile. So we have a nucleophile here that just needs deprotonating. Once we deprotonate this thiol, we have a sulfur with a lone pair that can be nucleophilic. So this is our nucleophile. And then we can turn this into our acyl. These two groups here, they don't really actively participate in the chemistry. They're kind of just around. And so now it's just about connecting them to the actual reactive parts of our reaction. So if I'm making this my acyl, I need to add an acyl group. I have my acyl. So now we'll combine the other ones to make the nucleophile. So now I have my two reactants or my two starting materials. And these are the opposite connectivity than he did in the key, but they still work the same way. So you can review this or you can review that, but they both work. So now I have my acyl and I have my nucleophile. We can actually start doing the chemistry. The first thing we need to do is deprotonate our nucleophile so it's primed for doing chemistry. So we'll have some kind of base come in and deprotonate. That is going to give us the active form of our nucleophile. Now with acyls, we can always remember their partial charge because of the difference in electronegativity. Our oxygen is our more electronegative atom, and so it's more of an electron hog, so it will have that partial negative charge. Now, in having that partial negative charge, it means it's hogging the electrons from the carbon. So our carbon will have a partial positive charge, making it a little bit electrophilic, which means our nucleophile is ready to attack. So that's what it does. And that pushes electrons up onto the oxygen. So now we have our two pieces connected. And this is what we call a tetrahedral intermediate. They're relatively unstable, so they're going to fall apart pretty quickly. These electrons are going to push back onto here. They're now on this carbon. So they have three directions they could go. If they went this way, they would kick off that carbon group. But that carbon group is not stable on its own, so it's not likely to be what's kicked off. If it kicked off the sulfur, what would be the point of clicking them together just to take them apart again? We wouldn't see any chemistry happen. So the only real place left to go is to kick off our phosphate group. So now we have our final product here. This phosphate would undergo protonation to give us this form. And we have successfully completed our acyl substitution. Yes, but that's not really a major step that we care about because the major product that we formed is already neutralized and complete. We just connected based on the squiggly lines. Oh, the first and the third. We needed an acyl, so we had to add an acyl. Because to do acyl substitution, you're gonna need an acyl.
So we just add.
Yes. Yeah. And so I think this is the second kind of question he's given you like this with the kind of squiggly lines with R groups. And the real thing there is these R groups are like decoration. Like they aren't active in the chemistry. It's, can you look past all of the distractions to actually see what's actively participating in the chemistry? And so if he gave you like groups like this and asked you to do any of the reactions that we have in our repertoire, you should be able to take those R groups and click them onto the actual reactive parts of the molecule so that you could make whatever reaction using these fancy R groups.
In the step on the bottom, like you said, there's 3 places the electron goes.
Yeah.
So the one at the top, it doesn't go there because you can't like there's no reason to do that. What was the reason you couldn't do the one on the left?
It would create an anion, a carbon anion, and there's nothing to stabilize that. So that would not be energetically favorable to create.
But it's okay to create like an anion with sulfur oxide.
So you wouldn't create it on the sulfur because then you would just be moving backwards to the nucleophile we already had. But electronegative atoms or heteroatoms, so basically everything that's not carbon and hydrogen, do a lot better job of being stable with a charge without having something else to hold them stable. So like when we have carbon charges, that's where we'll often see the need for a cofactor like PLP or thiamine or NADH. Other questions?
We review like amine creation.
Do you want to do amine formation with PLP or amine formation like in general?
So the one on the review, it's amine formation and transamination, which one was part of it?
So PLP does amine formation to change the chirality of amino acids. So it does transamination reactions where the amine connects PLP to the enzyme, and then it does a transamination to connect PLP to the amino acid. And then that's how it holds on to the amino acid while it plucks a hydrogen from the front and adds it onto the back, changing the chirality. Yeah.
Is that the taunt?
That is technically different than tautomerization. Tautomerization happens without the help of an enzyme. This is changing the chirality with an enzyme. Tautomerization won't change chirality, usually, for your purposes. I don't know what will happen with the cofactors. Yes, the last homework.
I know like thymine and PLP are
Cofactor is a molecule that participates in the reaction but isn't used up. So it, like NADH isn't really a cofactor because it changes to NAD. But thiamine and PLP are like, they stay the same at the end. They're just there to like, they're like, what is that stuff called on a side of a building? Structural scaffold. They're like scaffolding. They help keep it stable for the time being, and then when it's done, they go away.
So on your study guide,
Yes.
do either of these, I don't see PLP. You don't really.
I didn't put PLP or thiamine on the study guide.
just like.
I would say be able to recognize them and know what reactions they play a role in. So thiamine is going to be with decarboxylase. PLP is going to be amine formation for the purpose of changing chirality. And NADH, NAD is used for oxidation reduction.
People have to do, like, if you think we have to, but, where like it gives us the sequence of the peptide drawn out.
He could give you a small one like Rain or Chem. He's definitely going to give you the amino acid table if he does that, because you definitely are not expected to memorize the amino acid structures at this point, or the R structures. I would say know the general amino acid structure, like of just a normal like okay, you need a carboxylic acid end and you need an amine end.
What's on our last one? You can draw it out.
Yes.
Yes, I did it yesterday. I want to try not to do stuff twice if I have it recorded. I could go through Chem if you remind me what problem set it is.
I think it was 8.
8. Okay. So the first step is identifying what amino acids are being referred to here. So C is cysteine, H is histidine, E is glutamine, and M is methionine. So honestly, before you even look at your R groups, you can do the backbone structure of an amino acid sequence clicked together without even putting in your R groups. So you can just think, okay, this is 4 amino acids, or this is 5 amino acids. I'm going to draw 5 amino acids clicked together with the R groups and then just fill them in later. And that is how I'm going to approach this. So you have that is your basic amino acid structure. And your R group will always come off here. So we have our acid and our amino acid. Wow. So when clicking these together, you're going to make amide bonds. An amide is where you have C double bond O to an N. And that's because if we line up our next amino acid, our OH and NH are right next to each other. So in the amide formation, you're going to lose water in the form of this OH minus. So when they click together, we can draw it out as so that's our baseline, our skeleton structure all drawn out. Yeah. No. So now we could go to our amino acid table and just fill in our R groups as we find them there. So with cysteine, our R group is CH2SH. with histidine, our R group is CH2 and then this 5-membered heterocycle. Glutamine is another name for glutamine is glutamic acid, so it has a carboxylic acid attached to it. And then finally, methionine has ethyl. Amides. Other questions? How do we feel about a peptide sequence? That's the like formal name for this.
You draw it like you did the. Figure it out. Carbon's going.
Oh, yeah. This is like the letter drawn version. Yesterday is like the structure with, so this is like explicit where I've drawn out every single atom. The other one is implicit where I'm implying carbons and hydrogens with the corners in my drawings. Yes.
Which part on the chain is the carboxyl?
So it helps you out with the naming. Carboxy termini is going to be your carboxylic acid, and your amino terminus is going to be your amino end. Yeah. Okay. Question 4 from homework 9. Which also, did I do that yesterday or?
So yesterday you did the PLP one, like the way you define the molecule.
Huh?
Like you use the molecules that were given in the PLP.
Oh.
And you use the kind.
Okay. I tried to check it, so I missed it, but you'll still be able to hear me. Are you sure? Okay. Oh, also, I just got a text from someone in my lab about an instrument. I promise it won't be long.
Oh, I actually learned how to do. What was the more?
I believe what they need more research right off the bat.
No, I'm also there's water money to still like just still every single day. Like down the line, it's 8 lane highway.
So I got.
I'm contributing that.
I know, I was thinking,
Unless I do.
one.
Yeah, so that's what I'm saying. No, but like my friends have like all of them.
So here, so
Oh, what do you want to do? I guess I've never done that. Well, not like a battery. Yeah.
Whatever you like, you should tell me that. Yeah.
Okay, I wasn't for industrial use, it's really relevant.
We also like, not be.
There's a USC upon reading labs in population journal.
Right? I think it's 3 years.
We know about odds. We want it.
I took it all.
I'm a freshman, but. Yes. Yes.
So when are you gonna graduate next?
I graduate whenever I want. Basically. I could graduate next spring, but I'd be at the 18-hour semester.
I'm leaning towards
Oh, yeah.
I'm back. That's one from another lab. He's one of our instruments, and he might have just broke it. It's like $1,000 needle. Yes, and it needs to be exactly flat because it spins at 750 RPM, and he bent it. Who? It's a mix of the university and like grants we've applied for. Well, no, his boss is gonna have to pay for it. The kid in the other lab, the other PI will have to pay for it. Anyway, where I've broken other people's stuff? No. I've broken like some glassware, but I've never broken an instrument. No. Why don't I make the test? Who's they? You mean Dr. Begley? He's in the position to make the exam because he's teaching the course.
I thought it was an undergrad student.
You're listening. Okay, so PLP formation. We're gonna have our amino acid, and it has a specific chiral center. That's what I thought. Here, let me go back and look. Yes. Hallie, we did do PLP. This is all PLP.
Wait, which part is PLP?
We did thiamine in office hours, but not recorded office hours. This here that's labeled. Okay, so I'm not gonna go over this in detail because you can watch the recording. Do you want me to cover the thiamine stuff then? Okay. That's okay. So thiamine is, I would say, easier than PLP. But I guess that is in the eye of the beholder. So thiamine does decarboxylation. When I say decarboxylation, I mean the loss of CO2. So we'll start with this molecule. I'm getting there. Thymine is one of the cofactors.
What does that mean?
What does it look like?
I'm about to draw it.
Cool.
So a cofactor it means it participates in the chemistry as like a stabilizing agent, but it's not necessarily an active participant. Like it doesn't get changed.
So it just kind of hangs out.
Yes. So like I said earlier, it's kind of like a scaffolding that helps keep things stable. So like thymine is going to help stabilize the carbon anion that we're going to create in the decarboxylation.
Okay. Does that mean that the interaction reaction gets spit out, or is it just?
Yes, it gets spit out in the same form that it was put in. And PLP is the same way, where it gets spit out the same way it got put in. So to do our decarboxylation with thymine, you have to have an acyl group that's adjacent to a carboxylic acid.
That's what an acyl group is again? Is that like ketone, right?
How many times have you asked me
Oh, I've asked like 10
I
times.
second that question.
that? That's okay. This is an acyl.
You're like,
Oh, okay, so double bond.
Yes. A lot of oxygen. So I'm going to draw out the structure of thymine here. So this is the structure of thymine. The first step for our decarboxylation is deprotonation of our carboxylic acid. So we're going to go from carboxylic acid to the carboxylate. And for that, we're just going to need something that can deprotonate. Yes. And if you lose points for it, submit a regrade request, because I have just now explicitly told you that it's okay.
what is it? Excellent.
Yeah.
X minus I use as a general base. Base.
Base, okay.
Yes, I do the regrade requests. I don't do your first like initial grades, but I do handle all the regrade requests. So now we have our anion, and now we are going to get TPP involved. So like I have said before, with acyls, we have that difference in electronegativity that's going to give us a partial positive on the carbon of the acyl and a partial negative on the oxygen of the acyl. So that means that this center is going to be a little bit electrophilic, which means our nucleophilic thymine can attack and push the electrons up onto the oxygen. Acyl substitution requires an acyl and a nucleophile, and aldols require 2 ketones / aldehydes. So now we have our thymine attached to our substrate. And that thymine is going to help stabilize the anion we are about to create. So we're going to push the electrons from this oxygen in. That would overload this carbon, so we need to push these electrons off somewhere. So we're going to push them into that carbon center to create an anion. And in doing so, we have successfully decarboxylated. I don't think you should have to memorize it. I'd give you partial credit for it. Because it shows that you know the concept of what thiamine is helpful in doing and how it participates in the reaction, just that you don't have the structure memorized. And that's like half of knowing it, is knowing what it does. Decarboxylation. So now we have this anion here, and we are going to push, no, we're going to protonate. So now the last step is just to kick off our thiamine. Kick that off, kick that off. So we'll get our thiamine restored to exactly as it was before with the Zwitter ion state. Who remembers what a Zwitter ion is?
Oh, what? I remember the last time you said it.
It's a positive and a negative. So a Zwitter ion is a molecule that has both a positive charge and a negative charge all in one. So you can have amino acids that are in Zwitter ionic forms where the amine is protonated and the carboxylic acid is deprotonated. So you have a minus on one side and a plus on the other. Thiamine is another example of a Zwitter ion because it has that negative at the top and it has the positive on the nitrogen. But yeah, with that, we release our final product. And I kind of went in a circle here, but oh well. That's thiamine-dependent decarboxylation.
So the overviews, you're just losing one molecule. Is this about one? Not really. So it's something about one H2O, there's one H2O.
Are you talking about fatty acid biosynthesis where you lose a carbon dioxide? Because you're also losing a carbon dioxide here. So those are similar, but water is not involved. No. You can generate water with an aldol condensation or with an elimination reaction where you're eliminating a hydroxyl.
And hydroxyl is just OH.
Mhm.
The box thingy is protein biosynthesis, right?
Fatty acid biosynthesis.
It uses, can we go over how many of what it uses, you mentioned in the book? Like,
I'm going to give a really general overview. I'm not going to draw any molecules. Actually, I'm not going to draw any fatty acids, but I'll draw the starting material. So fatty acid biosynthesis is 4 steps. You have a Claisen-like reaction, a reduction, an elimination, and another reduction. Both reductions require 1 NADH. You will generate 1 carbon dioxide with every round you do. So the starting material is acetyl-CoA and malonyl-CoA. And your first round will hook those two together. Every round after that is going to add on a malonyl-CoA that's been decarboxylated. So you add 2 carbons with every round, except the first round, which is 4, because you added 2 to 2. So every round adds 2 carbons to your chain. It generates 1 CO2 and it uses 2 NADH. I hope not, for your sake.
That's when I turned a blank piece of paper and
So,
failed the class. Actually, I did it. Then you go, I was like, please, just, please. Show it to me, just answer me.
Unfortunately, I will not be proctoring your final. I proctored the extra time final. I proctored the extra time final, so like I'm not even in the like actual final with you guys. It'll be other grad students. Or what if you guys just like what if you guys just like studied and we didn't have to cheat? That'd be so fun.
How big is it?
6 to 8. Yes. It'll be like the length of your other exams. What? I don't know if I would say encompasses. It's like a good starting point, and it definitely covers like everything, every detail you could possibly need to know about the reactions. But I want to caution you, like, don't just memorize that study guide, because you're not going to get simple versions of those reactions. They're going to be convoluted in bigger molecules. And so it's about recognizing the pattern of those mechanisms rather than recognizing that specific structure. So like recognizing that an acyl substitution, you need an acyl group and you need a nucleophile. For electrophilic aromatic substitution, you need an aromatic system and you need an electrophile. For amine formation, you need an amine and an ester, question mark? I don't know, it's on the study guide. And for transamination, you need 2 amines. Or well, you need an amine and an amine, and you'll flop them. Yeah. If I had to guess, it's gonna be like the other exams where it's out of 150, and then he's just gonna multiply your points by 2. If I had to guess, the exam is gonna be like your other exams where it's like 150 points, but because your final is worth 300, he's just gonna multiply it by 2. But I don't have a lot of details. I actually have no details because I don't know what's on the exam.
Do you think we are cooked?
No.
Do you like that system? Or do you wish we had more problems?
You would not have done any more problems.
What do you mean?
Like, do you like how he does it?
Yeah, I think it's fine. Sure.
We got Dr. Stein.
Would you do open-ended exams?
For a class like this where it's like a survey of the information, probably. But if you guys were like pre-med or pre-vet, I'd be like, no, you need to know this.
I'm like, you know, my binder out.
Like, because we're all pretty bad.
Yeah.
Free farm. Free housewife, actually.
So you might be
Oh my God. Still waiting on that one though. So bad.
Yeah. Bye forever, because I will probably never see you again.
Okay.
And that was really sad.
Well, I'm not gonna see you at proctoring the exam, so what?
Are you gonna start class?
Yes, I'm proctoring the other exam.
No, but are you gonna miss for class?
Oh,
She said, yeah.
you guys are in my PowerPoint. You wanna see my PowerPoint?
But every year we'll let me like highlight of like.
They show the email, police emails.
Wait, where's us? Where's our pictures? Yes, I really hope you can. I really hope you get to see the. Comments. I actually think it's very interesting.
You know what's in the.
I love like this person. It's great. I love this.
Okay, I'll write you a nice email because you can't read our. Of course,
Just
this
me,
is.
Charlotte.
To quit.
It's okay, I'll add one. Right at 3:01 p.m.
I'll be still proctoring the extra time.
But then you could see it. Wait, when did you finish? When did you finish?
Whenever they finish taking the exam. He's not super strict about extra time.
Okay.
I think he's not really strict about the regular.
Do we have other like science questions, or are we just shooting the shit now? Okay, then I'm gonna stop recording this.
You just want to get to know you better. We just start watching.
Do this.